Hello and welcome to video number 17. Today we're going to be talking all about rotational stuff, moment of inertia, rotational angular momentum, rotational velocity, all that stuff. So let's get right started. So first of all, there are going to be a lot of relationships between the linear kinematics and the angular kind of kinematics. So there's for linear, there's velocity, or let's start off with something like distance. So that'd be x, then for rotation, be theta. Then we have velocity, we have angular velocity, we have acceleration, and we have angular acceleration. We also have mass, we have a moment of inertia. So that's the mass kind of for a rotating object. And that means that it applies to a lot of other things too. Like, for example, force is equal to MA. MA is I times equals torque. So you see there's lots of similarities with rotational kinematics and linear kinematics. So let's also angular momentum. We kind of talked about that. That's very similar to momentum, except for so that's mass and velocity. Except for angular momentum incorporates mass, velocity, where mass is inertia, velocity is that, angular velocity, and then all that times r. And that is equal to L. L represents angular momentum. So now that we've covered that, we're going to see how we can incorporate that into a problem and how it'll help us solve it. So here we have one. This is a relatively common problem. We have two disks. One of them is rotating here with angular velocity. Mass m and radius r, so this one has a mass of m, radius of r. Both of them have a radius of r. Rotational disk has moment of inertia of m r squared over 2. This one is rotating in a counterclockwise direction. There's no contact with the disks. Then the second disk is dropped onto the second one, and then they rotate counterclockwise, and they actually have a new velocity, which we'll call angular velocity F for final. So which of the following properties of the two-disk system must be conserved between the time the second disk is dropped on the first disk and the time the two disks began rotating with the same speed? So we're going to talk about a little bit of angular momentum. Acceleration, and then R. So angular momentum is actually the only thing that's conserved because we know that there's no external, since it's a closed system, there's no external factors pushing it in. So we know that this is conserved. Now, as for kinetic energy is lost as it does rotate. Actually, no, kinetic energy is conserved because there is, after the two have combined, there is a new mass. So therefore, it is conserved. So both are conserved, which would be option C.